Hey guys, welcome back to the Vintage Television Alignment Series. In this installment, let's talk about the front end, the tuner. I'll go over some theory, some block diagrams on the whiteboard, and then let's wrap up that Admiral 20B1 chassis, and I'll conclude by showing the overall performance after the alignment with test patterns and some programming material. Alright, now as before, I tried to simplify things as much as possible while retaining the key concepts. So it might not be 100% technically accurate, but it should get the idea across. We have three major blocks in every tuner. An wideband RF amp that amplifies the incoming signals from the antenna. We have a local oscillator, which is tied into switchable tank circuits for the channels you want to receive. We have a magical device called a mixer that spits out a signal that goes to our IF circuitry. Alright, so I've reduced this. Let's pretend we just have three channels in our broadcast area. Channels 1, 2, and 3. And in the FCC's wisdom, they decided that these would be on frequencies 40, 50, and 60. So we want to be receiving 40 megahertz on channel 1, 50 megahertz on channel 2, and 60 megahertz on channel 3. So this would be your rotary switch here. That's what this is supposed to diagram. So right now I'm set to view channel 1. And let's say our IF frequency is centered around 20 megahertz. So depending on which way the switch is thrown, we want this circuit to pull a certain frequency out of the air, and only that signal will be coming out of here, but it will be shifted. So 40 is going to get shifted to 20, 50 will get shifted to 20, 60 will get shifted to 20. Now, how does that happen? Well, a mixer is a device that will take two incoming signals and both add the frequencies together and subtract the frequencies. Now, RIF is lower than any of these channels, so we're not going to be adding two numbers together to get a smaller number. We're going to have to subtract. So what do we subtract from 40 to get 20? 20. So we would want this tank circuit to cause the local oscillator to run at 20 megahertz. So that will mix an incoming signal at 40 megahertz with the local oscillator running at 20 megahertz and give us the difference of 20 out. To receive 50, we want this to be running at 30 megahertz. So we would choose our inductor and capacitor values to resonate at 30 megahertz, and then that would only mix. So in other words, if say we have a signal coming in at 40 megahertz and this is running at 30, the difference will be 10, and our IF circuit is optimized for 20, so anything above or below that will get rejected out. Now there might also be a switchable bandpass filter as part of the RF amp, but it's not going to be a perfect bandpass that will block everything out. It might just attenuate frequencies, say above and below 40, a little bit. It's not going to eliminate them completely, so that's why you really need the IF. So this will reject outside frequencies somewhat. This will do a much even more complete job of that. And for the last one, to get 60, 20, we want this to be running at 40 megahertz. And yes, I chose the wrong color. 40. So inside the tuner, in that rotary drum or however it might be, there will be switchable inductors and capacitors, very stable factory preset for these frequencies. And then there will be some sort of fine-tuning control, which will be typically a variable capacitor that will be put in parallel with whichever one of these is switched into the circuit to allow you to fine-tune this capacitance a little bit. Also, often there is an adjustable slug for each of these, You can get a special tool in there and tweak these inductors a little bit to take care of that. Now there are some cool sets. Dumont in particular comes to mind where they had continuous tuners. So just imagine, instead of having a switchable inductor and capacitors for each channel, you just had a device that had, in their case, they have roller inductors. So imagine you had a fixed capacitor, but you had an inductor that you could rotate with enough range, you could cover the entire channel spectrum. Or even some sets that use variable capacitors to do the same. So that's the gist of it. So how does a mixer actually work? Oh boy, I gotta think back over 30 years to college. I believe any nonlinear device, like a diode, can form a mixer. This type of mixer is a ring diode, where they take 4 diodes, kind of like a full bridge rectifier, and you feed in your 2A signals into the full bridge rectifier at certain nodes, and it spits out the difference. So that's the heart of it. You have amplified signals coming in. You pick your local oscillator frequency very carefully. You have a mixer, and you get out the magic IF frequency that you need. Let's wrap up this Admiral 20B1 chassis. We left off with aligning the sound. The last thing I want to do is the RF front end and check the overall response. Then let's look at some actual test patterns and programming and see how good a job we did. Now, I don't recommend you mess with the tuner unless you absolutely have to, or you want to do some experimenting and don't mind if it gets a little messed up. So why might you need to align the tuner? Age, maybe. Most of the parts in here are ceramic and very stable, so I don't think that would be much of an issue. However, they do give one reason in the service info, which is if you need to replace the tubes, specifically this guy, the 6J6 local oscillator mixer tube. When you're dealing with the higher channels, channels 11, 12, 13, we're talking over 200 megahertz. And the inter-electrode capacitances will affect the frequency of the local oscillator. So if you switch to a different brand tube, different internal construction, it can throw out the local oscillator a bit. But even the manufacturer realizes what a pain it is to align these, so they suggest if you have to replace this tube, try a few different replacements before you resign yourself with having to tweak the alignment. At least the instructions are simpler. We don't need that minus 4.5 volt bias on the AGC bus. Instead, we just short the AGC bus to ground. We don't need a grounded shield over the 6J6 tube. Instead, we're going to be feeding our signal in to the antenna terminals. And we don't need that RC network after the detector, because we connect our scope or display device to this little loop sticking up here on the tuner. What we're going to be adjusting are these piston caps. Let me set this down and briefly explain why you don't want to mess with the tuner if you don't have to. So unlike the circuits we've already messed with that run on 20, 30, 40 megahertz, this can be several hundred megahertz. I'll pop out one of these and show you what they look like inside. This is a turret tuner with sections that pop out. They have a couple for each channel. The front part is the local oscillator. On this we have some inductors, which are just a turn or 2 or 3 of wire around this form, and there is a brass slug in the end that you can adjust. That sets the local oscillator frequency for this channel. If you were to disturb this wiring, move a couple turns closer or spread them further apart, you're going to throw off the alignment. Some more budget-minded sets, like Admiral TS-18 chassis comes to mind. To lower cost, they just have a rotary switch for the channels with exposed lugs, and for the inductors, they just have coils of wire just out in the open. If you bump into one of those while you're soldering or something like that, you're going to throw off the alignment. So I generally don't go anywhere near this area unless I have to. However, if you just want to check the response, that is a safe thing to do. So let's look at the instructions for a moment here. As I mentioned a moment ago, we don't need that 4.5 volt bias on the AGC bus, so you can remove that and you just short it to the chassis, which is ground. Disconnect any antenna you might have attached to the receiver. Allow your set and equipment to warm up for 15 minutes. Now we definitely need a sweep generator. This is going to be a little bit different. In this case, we will not be using a fixed RF generator, and we're not going to be peaking coils. This is a purely visual type alignment. There are 3 piston caps that we can adjust. A11, A12, A13. We will be adjusting them so their curve looks like this, with the sound and the carrier, the video and the sound carrier near these peaks, and the dip shouldn't be more than 30%. If it's off, adjust those 3 components, and good luck. They don't give you any indication on how to adjust them, or which one to adjust if the pattern is a certain way. You're just going to have to try it. That's why I caution against doing this, because you can get lost in the weeds pretty quick. It can be very non-intuitive how to adjust these. They interact with each other. But we'll give it a try. They talk about loosely coupling a marker generator. Yeah, if you don't have a sweep generator with built-in markers or support for an external marker, you can use this old trick about laying an RF generator near the sweep generator connections on the antenna terminals. And then we connect our scope or display device to point W. They do recommend using a 10K resistor in series with that loop to prevent your scope from loading things down. And finally set the contrast control to the center of its rotation. So we will be grounding this point and connecting our sweep gen to the antenna terminals. Now, the antenna terminals, 300 ohm twin lead. My RF generator, I believe, is 75 or 50 ohm output, so we have a bit of an impedance mismatch there. I've directly connected it without this, and it seems to be okay, but you might want to try using this as well, which is a 75 ohm to 300 ohm adapter. And throw a 10K resistor on this and hook up our scope, and that's all we need to do. So I will get all that set up, and we'll give this a try. Here's my test setup. I opted to just clip the output of my sweep gen right to the antenna terminals. I didn't bother with the 75 to 300 ohm balance. It seems to work fine. Likewise, I didn't bother with the 10K resistor. I tried it both with and without. It seemed to make no difference whatsoever. So here's what we get. I am on channel 12, as they indicated to start out with. It's not terrible. Here's what they show as the ideal response, and remember in the service info, the lower frequencies on the right, it sweeps from right to left, mine's going left to right. So they show the video marker being a little bit on the inside of the peak. Mine looks to be a little bit further towards the inside than what they show, but it's so close, I don't think it needs to be tweaked at all. And the 30%, yeah, I think that's within 30% about the trough versus the peaks. Well, this is channel 12. Let's try channels 3 and 4. Here it is on channel 4. And it looks rather odd. Let me double check with some markers. So let's put one at 67.25. That's down here. I'm going to show the one should be 71.75. It's over there. So it's misshapen, but it's in the ballpark. Let's check channel 3. Similar deal, also a bit misshapen. Let me see if I can tweak these a little bit. So 12 was pretty darn close to ideal. And they say if it looks good at 12, it should be good for the rest. Because there's really no adjustment I can make for these unless I can tune the individual oscillators for each channel, but I can't change the response for each channel. So what they say to do is that if it is off for some, to do the compromise. So if I make it better looking on this channel, it'll probably look worse on channel 12, but that's the compromise. But as I say, my customers typically use channels 3 and 4, so let's optimize it for 3 and 4. I want to have 2 markers though, so I am employing the tiny SA for a second marker, just laying the whip antenna near the antenna terminals. So I now have 2 blips on my display. One on the right is video, the left is audio. I discovered that the trimmer in the middle lets me shift the overall response. So it had been more like this when I started. I go on clockwise, I'm getting it to go more to the left. So that's about where I want to be, but I want to get that left side up. And that's where I'm at right now. Switching to a different one now, and if I rotate it clockwise, it's having a more profound effect on the right. You might think you always want to peak everything, but what I may end up having to do is to just lower the right side down, and the left side's going to stay where it's at. So yeah, I'm reducing the overall gain, but I'm getting a flat response. Now what would this translate to in the real world when you're watching it? What it would mean is the video carrier will be getting amplified more than the sound carrier. You can compensate for that by just turning the sound up. But the video, some detail is going to be amplified more than others. You probably would never notice it watching an image, but if you had a sophisticated test pattern, you might be able to detect it. Going counterclockwise. It's kind of getting me where I want, but I've almost backed the trimmer out all the way. Now I'm going back to the one I was messing with earlier. So sometimes you have to make it look horrible. Now I'm going to go back to the other one and put it clockwise and see where that takes me. Sometimes I've spent a couple hours doing this, just trying different combinations of things. There we go. I was just about to give up when I just kept at it. I had to take one slug and really back it out far. Tuning it back in a bit. So that's the one towards the front of the set. I had to really crank it out to lower the response on that right side. And it's actually really flat across the top, flatter than they indicate, but that's fine by me. Here's a test pattern on channel 3, and I really like what I'm seeing. Each band of vertical stripes corresponds to a different bandwidth. So for example, what I just turned off there, that is a 2 megahertz bandwidth. The finer the stripes you can see, the better. Typically, budget sets, you wouldn't see these. This is out to 4 megahertz out here. Meaning, if you can see fine stripes all the way for the wide stripes, and you can make these out very distinctly, that means you've got a full 4 megahertz bandwidth, which is outstanding. It's one of the reasons I like these early Admirals, is they have a very well-designed IF. Now that's channel 3. Channel 4 is the one that I really optimized for. Let's give that a try. Doesn't look so good. However, there is something else I probably need to adjust on this. Well, there's a little hole down here next to the channel changer. That is for inserting a tool to trim the local oscillator. I know I'd already done it for channel 3 because that's what I'm using for a lot of my testing. I haven't done channel 4 yet. Use a tool like this. It's a long fiberglass stick with a file down at one end to make a flat blade screwdriver. Now there's a 4th trimmer on the tuner I mentioned earlier. That sets the overall center of the fine tuning. It affects every channel. This will just affect this channel. Alright, here we go. I'm just going over a wide range just to see the effect. So it's interesting. It seems like I actually get better performance on channel 3 than I do on 4, or very similar. That's about as good as I can get it. Just focus a little. So yeah, we can see the stripes there. So that is a really outstanding bandwidth. We should get a really sharp picture. That's the best test pattern for checking bandwidth. I can go through a few others. Oh, here. So here's another curious artifact from the history of TVs. It's black and white TV. My test pattern generator does color. These are color bars. Look real close. I'll zoom in for you. Notice there are crazy dot patterns in each bar, and they're a little bit different. That's the color info. That's the color info that didn't exist when this set was designed. That's why in later sets they limited the IF bandwidth, because this is information that's out. So the color burst is at 3.58, so it's information that's towards the end. Later sets they cut off the bandwidth at about 3.5 megahertz. The set is pre-color, so it actually has better bandwidth than later black and white sets. That's color info. And there are some shows, Doctor Who comes to mind, where only black and white versions exist of color episodes from the John Pertwee era. They were able to colorize some of them because they were able to find the chroma dot patterns in the black and white film and use that to program in what colors to fill in different areas. So I'm not sure with this if I can turn off the color carrier or not. Oh, actually you just lose everything if you do. You can turn off red, green, and blue selectively with this. Anyways. Here's a good old crosshatch. So let's try some actual broadcast material. Still need to go through this set and adjust the height and width. Obviously we have too much height. I mean, not enough height. Now let's watch some actual programming. Now, I want you to keep a few things in mind. One, this is a set from the 1940s. It's meant, or it needs to be ideally viewed in a somewhat dim room. It's not an illuminized picture tube. It's lower high voltage than, say, Predicta. So this runs on 9,000 volts. Whereas the Predictas I've been working on lately are more like 15, 16,000. And they have illuminized picture tubes. They produce a brighter image. But this has better resolution. This also has no retrace suppression. And this has no DC restoration. So as scenes go from light to dark, you may need to adjust the brightness, the contrast, retrace lines may appear. So let's just focus on the image quality for now, which I think is pretty darn good. However, notice there's no sound. After I did the alignment and I fired this up, I thought I screwed something up, and I went back over it. And then I realized, that's because I'm using an over-the-air converter box, which is kind of cheap consumer-grade stuff. The way they modulate it, there's actually a couple points where you can get a really good-looking picture, but you don't get any sound. So let's try our fine-tuning adjustment again and see if we can get a good picture and sound. Now, if you look at the owner manual for these early TVs, they say to always adjust the fine-tuning for the best sound and just live with whatever picture you get. After doing an alignment, we should be able to get both to be pretty darn good. And you'll also find when these split carrier sets, there's a very small range where you get good sound. Versus the inner carrier sets where basically over the whole fine-tuning range you should get good sound. Alright, that's looking really good. We've got chroma dots, meaning I've got really good bandwidth, and we've got good sound.
Roger, attendant, you're on the bike. Roger, 112. Bike's registered to a Kenneth Rule, 19507 Oakhurst. No months, no hours.
Drop the brightness a little bit.
Roger, attendant.
Well, that is going to be it for my talk about aligning vintage stagger-tuned TVs and this Admiral chassis. If you are working on a set like this, and after you do the recap and check your tubes and all that, if you're not happy with what you see in here and you have the equipment, I would start out by aligning the sound. It's the easiest thing to do, and it's not uncommon for it to be off in a split carrier set. If you're still not happy with things, move on to the video IF, and only as a last resort would I suggest messing with the tuner. Next up, I will do, I think, a Predicta chassis alignment that will be inner carrier and the more modern 44 megahertz. I will be able to try using a B&K 415, and at some point I will try to use the Suncor SM152 I demonstrated a while ago. And lurking out in the garage, I do have some vintage Tektronix oscilloscopes, 515As in particular. I'll try using one of those. And as far as really vintage sweep gens, the only tube-based sweep gen I have left is an all-in-one Philco 7008, which I started restoring a while ago. I haven't looked at it in ages. I'm not sure where it stands, but I'll try. I'll dust it off and see what I can do. It is a combination sweep gen, marker generator, has a built-in display, and do it all, but not very well. It's my understanding, but we'll give it a try. I will leave you with some more examples of programming on the screen. Thanks for watching.